Is it understood what I'm saying? Whenever a process is created, some information about the process are being kept in a block. That block is known as the process control block or PCB. Right? This PCB is also known as the task control block or TCB, process control block, or this is known as the task control block. So this is for what? This is for every process that you are executing. For every process, there is a process control block. Correct? So each process is represented in the operating system by a process control block. What are the information the PCB contains? PCB contains all the information about a process. What are those? The state of the process. We have already read the state of the process, new, ready, running, waiting. So what is the state in which the process is currently in? If it is running, the process state must be running. So each of the state is being numbered and a number being assigned over here that represents in which state currently the process is. It keeps about the program counter, because while the process is running, it is executing the line by line, instruction 1, instruction 2, instruction 3, like that it is executing. So program counter points to the next instruction to be executed. So it keeps that which instruction to be executed next. This is a program counter. The process control block also contains a CPU registers. What are these CPU register? These contains the information of accumulator, index register, stack pointer, some general purpose registers. Those content of those registers are also being kept, because you are executing a program. That program might be using a index register, might be using some accumulator, stack pointer, some other registers might be using. Those informations are kept in the process control block. It also keeps about the CPU scheduling informations. It includes the process priority, pointers to the scheduling queues. It keeps about which process has what priority, and how which scheduling can be used over here. For that, the necessary information can be kept. So those informations are called the CPU scheduling informations. CPU scheduling means there might be multiple process. One of the process has to be selected. So which one will be selected, that depends on some criteria. Those informations may be kept over here. The memory management informations like the value of base and limit register, base table, segment table, etc. Those are also being kept. Process is kept somewhere in the memory. What is the starting address? How much? What is the limit of that process? How much memory it has taken? If it is in the page table, what is the address of the page table, segment table? Those are being kept over here. The accounting informations, amount of CPU time used, clock time elapsed since start, time limits, job number, these are also being kept. In the process control block, it also keeps about what? How much CPU time it has taken, how much clock time elapsed since start, what is the time limit, the job number, etc. Those are also being kept. It also keeps the IO status informations, the list of IO devices allocated to the process and list of open files. So just see over here, the process control block keeps track of what? Many things over here. Not only this, there are other things like a pointer to the child processes, a pointer to the parent process. Those are I have not written over here. Those are also being kept. Suppose a process has some child process, then that the address of those child processes are also being kept. Addresses of those child processes are also being kept. And not only for child processes, if the process is created from another process, the address of the parent process is also being kept. So information, many of the information are being kept in the process control. So everything related to that process is being kept in a block, and that block is called the process control block. Do remember, this is very important. Process control block is there. What is process control block or task control block, and what are the contents? Okay. Now question is that why do you have a process scheduling? What is the need of a process scheduling? The objective of multi-programming to have some process running at all times to maximize the CPU utilization. What do you want? To have some process running at all time to maximize. We want the CPU to be busy. We want the CPU to be busy. Always CPU must go on doing something. So if you have multiple processes are there in the memory, so whenever any IO occur, event occur or waiting occur, CPU should not wait, should jump to another process for execution. So CPU we want for the maximum CPU utilization, right? To achieve this, the operating system schedule the processes in an effective manner. So suppose I have 4 processes are running, operating system schedule these processes, which one will execute in what order, so that CPU will always be in busy. Correct? So process scheduler selects among available processes for next execution of the CPU. Okay, there is a query that what is the difference between process scheduling and job scheduling? I have already given in one slide that processes are also known as the jobs. Interchangeably we are using over here, so it is the same, the job scheduling. We are also either you write the job scheduling or process scheduling, right? In one previous slide I have already told you that processes are also known as jobs. Maybe the first slide I told. Here jobs, and here in the textbook you just job and processes interchangeably, so you have a job scheduling, the same. Okay. Now see here, so what is your objective? Objective is to maximize the CPU utilization. Multiple processes are running. What is the order in which they must be selected and given to the CPU, so that CPU can be utilized for the maximum amount of time. So process scheduler selects among available processes for the next execution of the CPU. Try to understand over here one thing. Look into this diagram. This diagram is for one process. One process will go to new, ready and all this. When one process is in the ready state, that means it is ready for execution. Similarly, another process may go into its own ready state. There might be several processes, they might be coming from new to ready state. Like this, suppose this is example of a P1 process. So P1 process, when it will go to ready state, there might be a chance P2, P3, P4, P5, like a number of processes may be in the ready state again, in their ready state. So there might be a number of processes in the ready state. There might be a number of processes in the ready state. And what you can do here, suppose I'll say I'll say here you have a something like a queue kind of thing is being implemented, and you will have a number of processes over here. Suppose P1, P2, P3, P4, P5, like that number of processes are over here. Now these processes, what we can see over here, suppose I have these processes. Suppose here I have 6 processes over here. Now just think of out of the 6, because all these are in the ready queue. So to make the processor always busy, suppose I give process 2 for execution. It is executing, but any IO occur, pre-tape, scanf, that kind of thing occur. So at that time processor is not doing anything. So to make it busy, I will send some other process over here. Correct? So what is the order in these processes has to be selected? That will be selected by some CPU scheduling algorithms. Correct? So CPU scheduling, why the CPU scheduling algorithm is used? There are many criteria we'll discuss, but the time being you remember that there are many processes are in the ready queue. Some processes, one processes will be selected and it will be given to the for execution, and that algorithm which decides this, which one will be selected, is a CPU scheduling algorithm. Correct? Okay. So now look here. So operating system maintains the following scheduling queues. So there are some scheduling queues are also there. Scheduling queues. Correct? The first one is called the job queue. Job queue means it contains all the processes in the system. Any process enters the system is put into the job queue. Just look over here. I have not drawn the. Okay, job queue is like, the processes which are ready for execution are being put in the processes which need to be executed are put in a queue. So contains all the processes in the system. Any process into the system is put in the job queue, whether it is ready for execution or not. Whether it is ready for execution or not, any process that comes, it will be put in a job queue. Is that clear? There might be 100 processes wants to execute, they will be brought and they will be put in a queue that is called the job queue. Out of those, some will be selected and brought to the memory for execution. Processes residing in the main memory, ready and waiting to execute. They are how will you say it is ready? If the resources are available, it will now it is ready for execution. When it is ready and waiting to execute, they are put in a queue that is called the ready queue. Is it understood what I am saying? Any process that enters will put in the job queue. The process which is ready and we're just waiting for the CPU for execution are put to the ready queue. So ready queue is maintained by a linked list which points to the first and last process in the list, and each process points to the next process in the list. So it is like ready queue. Here you see, suppose this is the ready queue, you can see over here. This is the ready queue. You can see over here, this is the ready queue. Now there are multiple processes. This is one process, this is one process. There might be a number of processes will be there. Each process is being linked in a link. This is being linked in a linked list. You can think of, see, head is pointing to the 7, 7 is pointing to 2, 2 might be pointing to some other location. It is not pointing to anything, so it is being null. So there are two pointers, head and tail. Head is pointing to the first process and tail will point to the last process. Suppose I have process 7, process 2, process 9 and process 5 is going to be executed. So process 7, process 2, process 9 will be over here, process 5 and 5 pointer to point in the null. Tail will point to the 5 and all processes have a pointer to the next process. And this is the way the ready queue is being maintained. This is the way the ready queue is being maintained. Is that clear? The ready queue? Okay. So now, so first one we have job queue. Job queue is all processes enter, so we put in a queue, that is the job queue. Ready queue, which processes are ready for execution and waiting for the CPU, those are put in a queue. This is the ready queue, and we have seen that how it is in form of a linked list. There are several device queues are there. There are several device queues are there. For each device, a queue is being maintained. Those are called device queues. Processes waiting for an IO device is added into a device queue. Suppose, for example, I have a hard disk. Process 2, 5 and 7 is waiting for the hard disk, requiring the hard disk. Then hard disk will have a queue with the process 2, 5 and 7 waiting for it. Suppose I have a tape drive. Tape drive is requested by process 1 and 9. Then I will have a linked list for tape drive which have the processes 1 and 9 in the linked list. Correct? Just see over here. Just see over here. Suppose I have some devices like magnetic tape. I have there are two magnetic tape unit 0, magnetic tape unit 1. I have a disk unit 0 and a terminal unit is also there. I have 4 devices over here. All these 4 are in the device queue. All these 4 are in the device queue. Clear? So I have 4 devices queue. From this device queue I can see none of the process is requesting to magnetic tape because both head and tail is pointing to null. So magnetic tape 0 is presently not requested by any of the process. Magnetic tape 1 is also not being requested by any of the process. From this it can be seen that disk is being requested by process 3, process 14, process 6. So therefore a link is there to PCB3, PCB14 and PCB6, and PCB6 is pointing to null. Tail is pointing to PCB6. The tail is pointing to PCB6. Is it understood? So you can see over here, rather writing the process name process P3, process 14 and process 6. Here we have written PCB because all information of the processes are over here and head is pointing to the PCB. So I am saying process, that means we are actually pointing to this PCB. So everywhere the PCB is therefore written. From here it can see that PCB 5 or process 5 is requesting for the terminal. So device queue, a device queue or IO device queue that is being maintained for every device present on the system. So each of the device what is pointing to the processes those who are requesting it. Any doubt on this ready queue and device queue? Any doubt on this ready queue and device queue? Okay, so processes migrate among the various queues. The processes migrate among the various queues. What the processes do? The processes, some process, suppose the process, we can here 765. Suppose here PCB2, here I can have a PCB2 also. That means PCB2, in these two I have PCB2, then PCB2 is requesting disk, PCB2 also requesting the terminal. A particular process may be requesting multiple number of devices, and that is being added to the pointer is pointing to that device, to that PCB as well, right? And these processes migrate among the various queues. Now it is requiring the disk, sometime it might be requiring magnetic tape, sometime it requiring terminal, so it migrate among these devices. Is that understood? So now let us go for, this is a very interesting diagram, is the representation of the process scheduling. This diagram is known as the queuing diagram. Queuing diagram. This represents what? This represents the queues, resources and flows. How, what are the different queues, how the resources and the flow of this. Correct? Now look here. Now look here. I have the process is entered into the ready queue. Try to understand. The process is entered into this ready queue. Correct? This is the line through which it is being entered. This is the line through which it is being entered. Correct? Now from the ready queue, it will be given to the CPU for execution. From the ready queue, it will go to ready queue means where? In the ready state it is there. So from this, it will be given to the CPU for execution. So it is executing in the CPU. Suppose it has executed all its line, means all the lines are being executed. Then it will go to exit, or we can say terminate. Is it understood? So the process which is in the ready queue is given to CPU and all instructions are executed, then it will go to exit or terminate state. This is state work. There is nothing to be done. But during execution, not necessary that all the instruction will be executed at the same time over there. There might be some problem or some IO occur, some event. So So now what you have, see here, this is CPU, ready queue to CPU, and it terminates over here. There might be a chance some IO request may also occur. While your program is executing, some of the statements are, suppose scanf statement. Scanf requires a keyboard or not? Input device is required or not? So if any IO request occurs, see over here. If an IO request occurs, it goes to what? It goes to this IO request occurs, it will be added to a IO queue. IO queue means input output, the device keyword is there, it will be added over there. Suppose it is requiring the keyboard, so keyboard queue, it will be added over there in the keyboard queue. Correct? At some point of time, it will definitely over IO completes, actually IO completes. Whenever IO event has occurred, means the keyboard you have given the input, then from it will be again added to the ready queue. It will be again added to the ready queue. Is it understood? So CPU is executing a program. A IO request may occur. If a IO request is occur, it will go to the IO queue. Whenever IO event has finished, when IO event is finished, at that time it will go again added to the ready queue for executing the or continue to the next instruction to be executed. In the meantime, when the IO request is being served, that time CPU might be busy in executing some other process. CPU might be busy in executing some other process. Suppose now process 2 has some problem of IO occur and CPU 2 is, process 2 is over here. So it might have sent the process 7. While executing process 7 also may occur some IO, or a time slice might be expired. Sometimes when the process is executing, suppose I am executing in a time sharing manner. In a time sharing manner, every process is given with a fixed time slot. Every process is given with a fixed time slot. So if the time slot expired, it will go for another process to attend. The processor will go to another process to attend. So if the time slot expires, then it will go to then it will come out, and again it will be added to the ready queue. Again it will be added to the ready queue over here. Is that clear? So if the time slot expired, it will be again added to the end of the ready queue. It will be added at the end of the ready queue, and during that time another process may be selected and it will be given to the CPU. When that process is executing, there might be a chance it may fork a child. It may fork a child means a new process may be created. A process might create another process. Those are called the child processes. Is it understood? A process may create another process. We will have in some of the lab experiments, we will do that, how the processes, new processes can be created. Anyway, so a process can, for the time being, you remember, a process can create another process. So if a child process is created, then parent process will wait, let the child will execute, and till the time it is executing, then parent may run along with the child, or there might be a chance the parent may wait till the child completes. So if the child executes, then it will be added to the ready queue, and in the meantime some other process may be given to the CPU. Similarly, while during the execution, there might be a chance the wait or for an interrupt may occur. If there might be a wait for an interrupt may occur. If the interrupt overs, suppose for example high priority process will come, then it has to come out. It has to be taken out. So it let the interrupt occur, and after the interrupt again it is being added to the ready queue. Correct? So this says that during the execution of the process, any of these four may occur. A IO request may occur, time slice may expire, it may fork a child, or wait for an interrupt. When this occurs, in action for the same, and some action are being taken, these are the action may be taken, and after that it will again go to the ready queue. for execution. So this process continuously being carried out, and when the last instruction is being encountered and successfully executed, it will go to the exit or terminate. This diagram is known as the queuing diagram. Anybody having now doubt on this queuing diagram? Any query over here, the queuing diagram? You may ask. Okay. We'll go for another some important concepts over here is called the schedulers. We'll have some schedulers over here. The operating system selects a process to be executed next among the processes present in the queue. This already I have told you. In a queue, there are multiple processes. So operating system has to select a particular process among many processes, and the control has to be given to the processor for execution. The selection process is carried out by appropriate scheduler. Which one will be selected? It is not a random fashion. This will be selected by a scheduler. Scheduler is kind of program which will select a particular process. Basically, we have three different types of schedulers present in operating system. Do remember, we have basically three different types of schedulers present in the operating system. Schedulers, for schedule means what? To select one among multiple processes, correct? So first kind of scheduler will say, although I have written short-term scheduler, we will start it from long-term scheduler. Suppose the first one of the scheduler is long-term scheduler. The long-term scheduler is called the job scheduler. The long-term scheduler is called the job scheduler. What it does? It selects which processes should be brought into the ready queue from the processes in the job pool. I have already told you about the job queue. Here in this slide, I told that job queue contains all the processes. There are multiple processes are there. From these, those who are ready will brought to the ready queue. Here it says long-term processes scheduler will does that. Selects which processes should be brought into the ready queue from the processes in the job pool. The processes in the job pool means in that job queue all are there. Which processes has to be brought to the to the ready queue. Long-term scheduler is invoked infrequently. Infrequently means it is not invoked very frequently, because once the process is brought to the memory and it is being created, process is being created, there is no work of the long-term scheduler. This is also very slow. Like, so long-term scheduler controls the degree of multi-programming. Degree of multi-programming means how many programs will be there in the main memory. So how many programs has to be kept? This will be controlled by the long-term scheduler. This scheduler is invoked only when a process leaves the system. Whenever a process leaves the system, there is a chance that another process will come. So in that case, only long-term scheduler will work. Correct? So once a process is being there in the memory, once if the long-term scheduler will put in the memory and create a PCB for the same, then there is nothing to be done by the long-term scheduler. So bringing the process to the ready queue, creation of the PCB for the same, only that much is the work of long-term scheduler. So in short, I will say long-term scheduler is responsible for creation of the process. Long-term scheduler is responsible for creation of the process. It will create the PCB for the process. It controls the degree of multi-programming and executed infrequently. Very less time it is being executed. Can it be remembered or is it understood or not? So what we have, the long-term scheduler takes the process, it will just put the process in the ready queue, so it is responsible for creation of the process and creation of the PCB for the same. Correct? So long-term scheduler is also known as job scheduler. This is also known as the job scheduler. There is another kind of scheduler is called the short-term scheduler. It's called the short-term scheduler, or this is known as the CPU scheduler. And among these scheduler, all these three kinds of scheduler I said, this short-term scheduler is executed very frequently. The short-term scheduler executes very frequently. What is the use of this short-term scheduler? It selects which process should be executed next from the processes that are ready to execute and allocates the CPU to it. It says that there are many processes is in their ready state. All those processes are ready to execute. Among those processes, one of the process must be selected, and that control of that process must be given to the CPU. But which process has to be selected? Which process has to be selected among the ready queue is decided by the short-term scheduler. Is it understood? Long-term scheduler selects what? From the job pool, not from the ready queue. From the job pool, which processes should be brought into the ready queue? That is long-term scheduler. Short-term scheduler says, among many processes in the ready queue, which process will be given control to the CPU? So sometimes it is only the sometimes the only scheduler in the system is the short-term, because long-term scheduler, once it will be done, and whenever a job leaves, then only the long-term scheduler will work. So sometimes only short-term scheduler might be working, right? Short-term scheduler is invoked frequently, and it is very fast because it has to select the process very quickly. As you can see over here in the previous diagram, all these things may happen. Whenever any of these things happen, another process must be selected and given to the CPU. Again, something happened, the next process may be given to the CPU. So any of these things happen very frequently, and in that frequency, if another process must be selected and given to the CPU. Once this is one of the, when one of the process exit or completed, another process will be brought to the ready queue, and bringing the process to the ready queue here, this we say as this is the work of long-term scheduler. This is the work of the short-term scheduler. Giving a process to the CPU, here a short-term scheduler will work. Bringing to the ready queue from the job pool is your long-term scheduler. I think these two are understood. We have another kind of scheduler, is called the medium-term scheduler. It's called the medium-term scheduler. Correct? So, what is this medium-term scheduler? It says in time-sharing operating system. Time-sharing, already I told you what is the time-sharing. Every process is given with a fixed time slot. So, in a time-sharing operating system, uses the medium-term scheduler, which removes the processes from the memory from execution by the CPU, store on the disk, bring back it from disk to continue execution. That means while execution, a process may be bring back to the disk, and whenever required, again it will bring from disk to the memory. This process is known as the swapping, and this is being done by the medium-term scheduler. Try to understand what the medium-term scheduler does. This will come into act whenever the program is brought from memory to disk and disk to memory, right? In that case, the medium-term scheduler will work. Correct? So these are the three different kinds of schedulers which is being used for selecting a particular processor job, either from bringing to the ready queue, or from ready queue to CPU, or to the disk, or disk to memory. Okay, now if we talk about the processes, there are two different kinds of processes usually we encounter with. Processes can be described either as a IO bound process or CPU bound process. The programs or the processes that we execute in our system, some of the processes are called IO bound processes, IO bound processes means spends more time during IO operation than IO than computations. IO bound means more IO operations, less computations. So spends more time doing IO than computation, many short CPU bursts. Short CPU burst. Short CPU burst means CPU execution time. So they have small execution time, more on IO computations. Is it understood what I'm saying? Some of the programs are there where more of the time it takes for IO operation, less time it takes for computation. There are some CPU bound processes as well. CPU bound processes. What are the CPU bound processes? It spends more time during computation and less time for IO operations. So very long CPU burst. One of the process might be taking much time for execution. CPU is very weak. So in IO bound processes, CPU is idle because they have short CPU burst. But in CPU bound process, most of the time CPU is busy because they have very long CPU burst. Correct? For example, if I say you input 30 numbers and find the sum. So how many instructions you have? 30 times 30 instructions will be there to input. Maybe you put in a loop or whatever. So 30 times it is doing the IO operation, maybe the scanf operation, and there might be one computations. There might be one computation or CPU computations. So this kind of process we say as the IO bound process. More on IO, less computation. I have 30 times I am inputting and CPU is computing for once only. But if I say you input two numbers and find their addition, subtraction, multiplication, division, average, and whatever, all those things you find out. So now what you have input only for two numbers. So there are less IO, but many computation you have addition, subtraction, multiplication, division, power, average, whatever you are computing. So more region, the CPU is busy for more times rather than the IO operations. Right? So this is just for overall I have given the example. The thing is that a process may take long time for computation and some processes are there which takes long time for IO operation and less time for the CPU operations. So long-term scheduler should select a proper combination of CPU bound and IO bound processes such that the system will have best performance. Is it understood? Which processes the long-term scheduler will select? The long-term scheduler should select proper combination of CPU bound and I found one process is CPU bound, another process is IO bound. If these two processes will be selected, then I will have better CPU utilization because whenever IO will occur, I may send the CPU bound process for execution. Whenever in CPU bound and IO is required, at that time I may send the IO bound process for operation. So we will have a combination of the CPU bound and IO bound process may be given. So who will select it? The long-term scheduler will select it by looking into the program nature. By nature of the program, the long-term scheduler will select that which process requires more CPU cycles and which will be required more IO cycles. Correct? So some operating systems like Unix, Windows doesn't have long-term schedulers. Some operating systems, they don't have long-term schedulers. They keep every job in memory for short-term scheduler. What they do, instead of keeping selecting some jobs and put it in the ready queue, they put everything in the memory. They keep every job in the memory for short-term scheduler. Right? So among these three kinds of schedulers, most of the time, if a particular scheduler which is working is the short-term scheduler, very frequently it's working. Medium-term scheduler will only come into work only when the process will go to the disk and disk to memory. Not necessary that every process will go to the disk and we have to bring back to the memory. Right? So once the process is selected by the short-term scheduler, Once the process is selected by the short-term scheduler, from this short-term scheduler we will select it and give it to the CPU. To connect to the CPU, a module is used over here. Try to understand. There is a short-term scheduler which is selecting one of the process from the ready queue and give it to the CPU for execution. So how it will give? It will give through a module called dispatcher. Dispatcher is a module which will connect the process selected by the short-term scheduler and connect it to the CPU. And connect it to the CPU. I have written somewhere that I will. So we have a short-term. Sorry, there is a dispatcher is a module. Dispatcher is a module which connects the process selected by the short-term scheduler, connects the process selected by the short-term scheduler and gives the control to the CPU for execution. So it is like a like a connector, a bridge. What it connects? One process with the CPU. So process is what? The process which is being selected by the short-term scheduler. This diagram is for the same. So we have batch of jobs from which long-term scheduler will select, correct? Long-term scheduler will select and put it in the ready queue. There might be number of processes in the ready queue. Short-term scheduler will select one of them and give to the processor. If it is executes, that is fine. If it is not, it may be suspended ready queue. It may be sometimes from the processor, it may given to the event queue or blocked queue. It may be from block suspended. It can brought to the ready queue. That in the previous diagram already I have explained you. So here actually your long-term scheduler and here your short-term scheduler works. Is the diagram understood? So before continuing, let me first take you attendance. Then we'll go for if you have any doubt. Roll number 2 is 4, 5, 13. 20.
सर सर रोल नंबर 13 सर, वो रीनेम नहीं किया था पिछला क्लास सर.
रोल नंबर 13. ओके. प्रेजेंट 22, 24, 25, 27, 30, 37, 44, 46, 73, 73. Sagar Mahanti, your roll number is? Hello, Sagar.
Yes, sir.
What is your roll number?
Sir, 20.
You should have written your roll number. 20.
Sorry, sir.
46 is present. Okay. Let me again tell the absentees. Roll number 2, roll number 22, 24, 25, 27, 30, 37, 39, 44, 49, 71 and 73. Is that 71 present. What is 71? Okay. Anyone else having any? I think this. Yes, I think it's everyone. 63. Okay, any doubt for this, for today's class? Any doubt? Then I will end the session now.